Hi, and welcome back. So, on the last video, we were talking about how to interpret um, problems of the task that a robot has to perform, and we solve a transformation equation. We write a transformation equation based on a task that a robot has to do. And I said that on this video we will solve the example 2.15, but I'm afraid that at the first moment this can be difficult to understand. So first we'll solve this example again to warm up, and I will try to emphasize on the more important parts. So let's jump in. Um, Again, in order to write a transformation equation which describes the motion that this robot has to perform in order to do some certain task, we need to know with detail what this robot has to do, what the task that this robot has to perform. So on this example, the task is to drill a hole on a workpiece. So right here we don't have a text uh, describing uh, what this robot is doing, but we know the task itself. We know the task is to drill a hole. So just from knowing what this robot has to do, we can already write a transformation. Um, so the transformation is um, the transformation of the frame E in relation to the frame U. And that means we wanted to know where where's the end effector is going to be at the end of the task. And we need to be able to understand the meaning this of this name end effector. End effector means uh, where the two responsible for perform the task. We know that the whole system, the whole robot is responsible for perform the task, but is going to be the end effector responsible for do the task itself. So where's this end effector is going to be at the end of the task, and we need to write this transformation with coordinates. We need to pass coordinates for this robot, otherwise we won't be able to know its localization, its orientation, its position, and how we can perform a task, and this type of task of drill holes, of grab objects, uh, record with a camera a object. We need to pass coordinates to the robot, and we do this based on a reference system, a reference frame. So that is the universe reference frame, which has coordinates on the 3D space. So we need to have a reference frame, and with this reference frame we write transformation for these other frames. So now we already write a transformation, which is the transformation of the frame E in relation to the frame U, the transformation of the end effector in relation to the universe frame. So what we are doing is track the end effector based on a reference system. And now, how we can know um, the paths that this robot is going to do? How we can know um, the motion um, for evaluate this transformation, um, which is where the end effector is going to be at the end of the task. Well, as this workpiece is a body separated from the robot, we can write a path. We have a path uh, which is independently of the robot. So we can write a transformation of the P frame in relation to the U frame. And that is because as we are not working with matrices, and that means we are not being precise on this task, we can ignore the sentence of whole right here. We can say that the end effector is going to be at the same position in localization as the workpiece itself. So we are not working with measures. If we were necessarily to pass coordinates to be able to localize the orientation and position of the drill to do the task. Okay, so where's the end effector is going to be at the end of the task is at the same localization as this workpiece. So we can write a transformation of the end effector in relation to the reference frame U. So is the transformation of the frame U in relation to the transformation of the frame E in relation to the frame U. And we have now to write an equation, a transformation equation based on the whole system. So right here, each frame it turns on a reference frame for the link in which is attached. So in the same way as we are writing, let's write this first transformation. We can write that as this frame of the robot is fixed, we can write the transformation of the frame R in relation to the frame U. And now this frame R it turned into a reference frame for the frame H. So we will write a transformation of the frame H in relation to the frame R. And now this frame H it turned into a reference frame for the frame E. So we write a transformation for the frame E in relation to the frame H. And that's it, how we write a transformation equation interpreting the task that this robot it has to perform. And now that we warm up, let's solve the example 2.15. Okay, example 2.15. Okay, so let me write the example 2.15. It says that in a robot setup, a camera is attached to the 50 link of a sixth degree of freedom robot. It observes an object and determines its frame relative to the camera frame. And ask to us to use these informations to determine the necessary motion um, that the end effector must make to get to the object. And now, different from this first exercise of write a transformation equation, now we have coordinates. Now we have matrices with coordinates um, to localize the object and the camera. And I'm already got um, I'm already adapted um, from the first example this design. So I attached a camera on the fifth link of the robot. So now it remains only to write the matrices. So let's write the matrices that this exercise provide as information. So the first transformation is that one. a camera attached to the fifth link of the 6-degree robot. So is the transformation of the camera in relation to the fifth link, and that is the first transformation. And those are for rotation and translation. And on the fourth column is the coordinates of the position of the rigid body. So is the coordinates of the camera in relation to the reference system X, Y, Z. And it observes an object and determines its frame relative to the camera's frame. So is a transformation of the object in relation to the camera. And again, you can see an example, the interpretation of the text, and base it on the described base it on the description of the text. We must be able to write the transformation. Okay, now writing the entries of this matrix. 0, 1, 0, 0, okay. This design is quite a mess, but we have to keep going. Only base it on the design in the task, and we know that the task right now is the camera is it has to observe an object. So based on this, we can write a transformation equation of the hand of the robot of the frame H in relation to the fifth link. So let me drag a little bit this H right here. And this transformation, now we are working with coordinates, and the entries of this matrix, which represent the, the motion of this transformation. The entries are these ones: 0, 1, 0, 0. Okay. And the other transformation is the transformation of the end effector in relation to the hand of the robot. So is the transformation of the frame E in relation to the frame H. So again, the frame H has turned it into a reference for the frame E. And its matrix, the entries of its matrix, they are 1, 0, 0, 0. Okay. And let's organize this so we can start to work. Um, those are matrices that was passed to us, was given to us, um, that example given to us. And which is was not provide, it was uh, the transformations, the interpretation of how to write these transformations. And those are not the only transformations that we can obtain uh, just interpreting this task of a camera observing this object. We can write others, and right now is kind of tricky. We will substitute this reference system for this reference system. So for this reference frame, so the universe um, reference frame, we will substitute for the frame of the robot. So the this R is going to be our reference frame. So right here we are substituting this reference for this reference. S is the link fixed of this robot. All those links, they are movable, but this link is fixed. So we are substituting this reference for this reference. So this robot frame, it turns into a reference. So is the robot reference frame. Right here we are substituting the frames, the reference frames. And right now we will write a transformation having this frame as reference. So is a transformation of the fifth link in relation to the frame R. And the other transformation that we can write is a transformation of the object in relation to the end effector. And now we can write our transformation equation. And again, we have to do a work of interpretation. So let's interpret this task. So as the object in observation is separated from the robot, we can write a transformation, but now different from the first example, the first exercise that we used to warm up on the beginning of this video. This reference universe, we are substituting for this fixed um, frame, this fixed link of the robot. And let me organize the terms of this transformation equation. So again, as this object is separated from this from the robot, so uh, it are two rigid bodies, and we have to write an equation for the whole system. So we have a one system, two system, three systems, and the uh, one system, two system, three system. Got it? Okay. So we are writing uh, a transformation equation. Let's first do for the object. And now we cannot write a transformation of this reference for this object because it is different from the first example. We are writing a transformation of the object to the camera attached to the fifth link. We are writing a transformation of the camera in relation to the fifth link, and a transformation of the fifth link in relation to the frame R, which is the frame for reference now. And those are steps that we can do in order to activate the task of the camera to observe this object. And now for this system of the robot, in order to perform this task of observe this object, we can write a transformation of the fifth link in relation to the frame R. So it's a transformation of the fifth frame in relation to the frame R. And we are writing a transformation of the frame H in relation to the fifth link. And as I'm already explained, one frame it turned to a reference for the other frame. So we are writing a transformation for the frame E, a transformation of the frame H in relation to the frame, a transformation of the frame E in relation to the frame H, and a transformation of the object of this frame in relation to the frame E. So this frame has turned into a reference frame for this frame. Now solving this equation, as this transformation appears on the both sides of this equation, we can eliminate it. And now notice that we cannot apply inverse transformations for for any transformation. We only can apply inverse transformations for transformations that are null. And right here on this equation, the transformations that we know, they are the transformation of the frame E in relation to the frame H, So we can apply inverse transformation for this transformation. And the other transformation that are known is the transformation of the frame H in relation to the fifth link. So we can apply inverse transformations for these transformations. So let's do this. Okay. And what we do on one side of the equation, we have to do on the other side. And we are doing this to simplify this equation. So we will be left with only one transformation on this side. Okay, so now eliminating these transformations. And we are left with the following transformation equation. Now applying the property when we got inverse transformation, we can rewrite without the superscript, switching the frames. Okay. And that's it. The transformation equation that describes the motion that this robot it has to perform in order to observe this object. Now we have to work with the matrices. So we got um, the coordinate of the transformation of the frame of the object in relation to the frame of the indefactor, the frame E. And we already has saw how to calculate the inverse of a transformation. So we have to calculate the minors, and with the minors assemble the adjoint matrix and divide by uh, its determinant, the determinant of the original matrix. And as is a laborious procedure, I will only pass to you the matrices with the answers. And as the example do not provides to us the information that the the transformations that are being performed, they are only simple rotations. We cannot tell, we cannot just transpose the matrix and calculate the product between the negative product of the vector P between the the vectors of the reference system NOA. Okay, so um, now um, as we rewrite the equation without the inverses transformations, um, we we don't need to worry with this detail of calculate the inverses. Um, those two transformations, they are known. We know these two transformations, and we use this property to get rid of with the superscript of these transformations. And the example also provide to us the matrices of these transformations right here. But as we use this property to get rid of the superscript, and we switch the frames, so they're going to be different. On these matrices, we have to use this system of signs. So I think it's better if I solve this with you. So let's solve. Um, we have this transformation, this one, And now we have to adaptate this the systems the system of signs, and we have just to intercalate the signs and add one more column. So intercalating plus minus plus minus plus minus minus plus minus plus, and now we have to apply this sinus on this matrix. So right here we turn it into a positive one because it's minus times minus, which gives us a plus signal. Right here is minus 1. And now for this matrix, the transformation of the frame H in relation to the frame E, but it was provided to us this transformation, and we switch the frames, as you can see, and we will apply this sinus right here too, and right here is minus 3. Right here is minus 1. Okay. So we have all matrices. And what we wanted to know is the position, the orientation, which resumes on the localization of the object in relation to the camera, which is attached on the end effector, whereas the camera is going to be at the end of the task. So we are tracking the position and the rotation of the object the whole time. And performing this calculus, we obtain the following matrix. And that's it. So again, we have to be able to interpret the exercise with the information that is given to us and interpret the task that this robot is doing. So the first transformation just right on the beginning of the exercise that we can extract from just by looking at the robot, what it's doing, and knowing the task is the localization, the position, and the orientation, which resumes on the localization of the object in relation to the end frame, which is where is the camera is attached. So we are tracking the localization of this object the whole time based on the frame of the end frame where is the attached the camera. And that's it. The next videos we will be talking about forward kinematics and inverse kinematics. And I think for now is out. Thank you.